Hello, so we're going to talk about Chapter 1 material. Chapter 1 is Introduction, the Nature of Science and Physics. This is a chapter that I have tended not to have given as much attention to as maybe I should have, because we're going to introduce some concepts that are a little bit out of context. And so I always thought that might induce fear into the hearts of students because they're learning about some ideas when they don't need them yet. But I have since come around to the idea that maybe it's important to introduce these ideas, and then when you see them again as we're using them, they will be less scary. So first of all, I don't know if you've spent any time in Meyer Hall, but after you grab your coffee, if you walk up that front stairwell, there's a mini history of Salem, Massachusetts, and I just want you to notice, I wish this would stop happening. I want you to notice that if you go up the stairs, the top right, the culminating event in the history of Salem, Massachusetts, is Dr. Meyer of Meyer Hall, the building that you'd be in, teaching, what is that, E = mc squared, teaching physics. That's the culminating event in the history of Salem, Massachusetts. That's pretty cool, huh? The language of physics. Physics is a little bit, what's the word, obnoxious, I guess, is maybe the word. Maybe one day the United States will make the big push and start using the metric system. We're kind of half-hearted about it now. We'll buy our milk in gallons, but our Coke in 2-liter bottles. So mass in kilograms instead of pounds. So that's mass in the units for the metric system is kilograms. And what makes physics even special in being obnoxious is that if you ask a chemist or biologist, they might be talking about mass in grams, whereas in physics we use our base unit as kilograms. So there it is. Time is in seconds. We'll do displacement, which is, in normal people speak, the same word for distance. That's meters. And then, therefore, if we have displacement in meters and time in seconds, we'll have velocity in meters per second. And then this concept called acceleration, which is how your velocity changes, and that'll be in units of meters per second squared. So Foxtrot Comics sometimes catches the sense of the language part. I think people get tripped up with the language in physics, and it's not English as a second language kind of issues. It's issues where physics uses terms in a very specific way, and you might be used to using those words in normal life, and now they mean something else, or they're just words you've never heard of before, and you're like, what are you talking about? So I'll try to help you through that. We'll make sense of this. It won't be so bad. Alright, so physics has developed out of the efforts of men and women to explain our physical environment. It encompasses a remarkable variety of phenomenon, everything from understanding planets to radio and TV waves, magnetism, lasers. Any technology that we're using has some foundation in physics. Any technology for human life, I mean, artificial hips and artificial hearts and all of that has some foundation in physics and understanding how these materials will work and what goes on with them. It all is founded in physics. So what we're going to be doing is predicting how nature will behave in one situation based on the results of experimental data in another situation. And for this course, a lot of what we'll be talking about are actual fundamental physical laws. it doesn't mean that they're always entirely true. We're going to simplify some things and then come out with the truth that, well, you know what, it doesn't really happen this way because there's air resistance or friction, but we'll get a real sense of things that you can see, touch, feel, experience in your actual life. But in order to go down that road, we have to do the tedious stuff. So physics will involve measurement of a variety of quantities, and those measurements should be accurate and reproducible. And the first step in ensuring accuracy and reproducibility is defining the units in which the measurements are made. So your first lab will involve measurements and uncertainty, and you will be using different devices to measure the width of something or the density of something, and you're going to get a sense of what's going on there with making accurate and reproducible measurements and then reporting your results. So it's the International System Scientific International, or System International, uses meters, kilograms, and seconds. Sometimes you'll see somebody list things as MKS units, and what they mean by that is meters, kilograms, and seconds. This is a meter. You can go to the National Institute of Standards in Washington, D.C., and there's a couple of different devices, couple of different places that have these benchmark things. So this is a meter, this is a kilogram. Weird thing, meters, we have a very specific definition based on some radioactive decay that we're really confident is always happening that way. We can define time that way, we can define distance that way. What we don't have is some real sense of mass. And so this is a kilogram. There were a few different kilograms that were set aside as here's our international benchmark, and they're kept really carefully. But it turns out now, sometime later, 100 years later, they don't all agree with each other. So we don't actually have a real great sense of what a kilogram is other than a sense. So it's a little bit troubling in the scientific community. All right, more stuff. So you're going to drive down the road at 65 miles per hour. All right, fair enough. So if you're driving down the road at 65 miles per hour, if you travel at 65 miles per hour, how far would you travel in 1 hour? Well, I know that. I knew that equation. Even if I didn't know it looking like this, I would have known it just from a general sense that distance, displacement, x, equals velocity times time. So the velocity is 65 miles per hour times time, 1 hour. That means that I would have traveled 65 miles. Piece of cake. Hey, how about 2 hours? All right, now I might have to bust out my calculator in order to do this. Maybe I can do this in my head. 65, so 60 times 2 is 120. 5 times 2 is 10. 130 miles. So if I wanted to do how far I would travel in 2 hours, 65 miles per hour times 2 hours. And I could do that. That's how far I would have traveled. How about 5 minutes? 65 and 5, I don't know. So here's one of the first things where we're going to have to pay attention to units. If we do velocity in miles per hour, we have to also do time in hours. If I wanted to do time in minutes, I would have to change 65 miles per hour into how many miles per minute if I wanted to be able to do that one accurately. So I remember when this happened. Maybe you weren't born yet. In 1999, NASA lost a $125 million Mars orbiter because half the project staff used imperial measurements. That's what they would use in Great Britain. And the other half used metric measurements. And the programming on the orbiter wasn't in agreement, and it sent it to the wrong orbit trajectory, and we lost it, which is tragic, but illustrates a point here that we have to make our units agree, or else we're not going to get any information that makes sense. So 5 minutes, we want to multiply that number 5 minutes by the number 1. And in order to do that, I set up this equivalency. Inside the parentheses here is the number 1. And the number 1 looks like this: 1 hour over 60 minutes. That's the number 1 because there are 60 minutes in 1 hour. So minutes cancels out. I have minutes in the denominator here. I have hours in the numerator. So minutes in the numerator cancels with minutes in the denominator. I get rid of that unit, and I carry out the unit of hours. So 5 minutes is 0.083 hours. All right, I guess that makes sense. All right, so if I do that, then I can go back to my first equation. Okay, so it's not 65 times 1 hour, it's not 65 times 2 hours, it's 65 times 0.083 hours, and I get 5.42 miles. You'll want a calculator handy. Sure, your cell phone is a calculator. Remember, you have to turn it sideways to get the scientific calculator. You'll need that eventually. For right now, we're just doing some basic arithmetic, so you could have it held the short way up. But you have to turn it sideways to get the scientific calculator. All right, so the units for length, mass, and time, as well as a few others, are regarded as base SI units, and we use those in combination to come up with other physical quantities such as force and energy. Sometimes we'll have to convert units. So I was doing stuff in miles before, and that's not what we're using in physics land for the most part. So if I wanted to get my answer in kilometers per hour or meters per second or whatever, then I would have to convert. So I'd have to know, okay, 1 mile is 1.609 kilometers. I say I'd have to know it. I do know a couple of these things off the top of my head, but I've also been teaching this course for a while. But I don't know all of these conversions off the top of my head. And you know what? It maybe is a tricky thing to think that I know it and then find out that I flipped the units in my head somehow. So you can look it up. You can look it up on Google. You can look it up in the book. You can look it up anywhere. Make sure you use the accurate conversion factors, but the point is that you have to know how to use them. So we were just told that 1 meter is 3.281 feet. How would we use that? Well, here's an example. The highest waterfall in the world is Angel Falls in Venezuela with a total drop of 979 meters. If we wanted to express that drop in feet, because we're talking to someone who doesn't really know how long a meter is and they just want to get a sense of that in feet, we'd say, all right, well, 3.281 feet equals 1 meter. So this is this equivalency. So 979 meters, I want to cancel out meters. I want to get rid of that unit and leave the units in feet. So 979 meters times 3.281 feet per meter gives me 3,212 feet. That's the drop of this waterfall in feet instead of meters. All right, metric prefixes. So we've already started off with kilograms. Kilo is 1,000. So 10 to the third power, that's 10 times 10 times 10. That is 1,000. So kilograms is 1,000 grams. And it's just kind of goofy that we use that as a base unit in physics instead of grams. But sorry, that's the way it is. In the whole wide world of science, in normal life we'll do kilograms. I don't think anybody does hecto anything, or deca or deci. Nobody does that. Centimeters, you probably have heard that before. Millimeters. Micro we'll use in very specific applications, so microliters or I don't know, other applications. Nano and pico are really, really tiny. You're probably not going to get there in your normal life. Everybody would love to win Mega Millions. Mega is a million. 10 to the 6 is 1 million. And then you get up into units that you only hear about in Back to the Future or something. So there's metric prefixes, and we want to be able to use them. So if we're going to convert between units, in all calculations, write down the units explicitly. We're going to treat them as algebraic quantities. That means that's where I was talking about canceling things out. That's what you would do with algebraic quantities. When identical units are divided, they are eliminated algebraically. Use the conversion factors located on the page facing the inside cover of your online book. Somewhere you will find your conversion factors, either in the body of the book or somewhere that you can download it, or just look them up as you need them. Just ask Google or Siri to help you. So here's our 65 miles per hour again. If we wanted to convert that to meters per second, we'd take 65 miles per hour, figure out how many feet there are in a mile, how many seconds there are in an hour. We get feet per second. I teach physics, my wife teaches chemistry. She would urge you not to do this all in one long stretch like this. I would urge you not to do that either. Do it one step at a time instead of one long stretch down the road, because people just confuse the heck out of themselves when they do it this way. What you could even do, which would be a ton easier, 65 miles per hour, you can look up the conversion factor to do miles per hour into meters per second and not do it step by step like this. All right, weird concept, dimensional analysis. I have found so often in my teaching career that people memorize equations when they don't need to, and what they do is they memorize them wrong. So x equals 1/2 vt squared. Sure, why not? Maybe that's a real equation. Why would I doubt it? It's written there on a slide. But it turns out that we're not comparing apples to apples. Have you heard that phrase before? Comparing apples to apples? So on the left here, the unit, what we're talking about is length. It's a distance. It would be in meters if we were doing it in normal physics language. 1/2 is just a number, so it has no units. Velocity is distance over time, and then time, when you square it, is time squared. So if we did this, we cancel the time in the denominator with one of these t squared ones, and we end up on the other side of the equal signs with lengths times time. So we have length equals length times time. That's just not true. Those units don't match up. That's dimensional analysis. It sounds so much more scary than it really is. It's just saying, is your equation not insane? So this equation, this is the one we've been messing around with. Distance equals velocity times time, because velocity is what we're doing. We're doing miles per hour. So distance over time times hours gives us miles. That makes sense. The left-hand side of the equal sign has a unit in distance, and the right-hand side of the equal sign winds up with a unit in distance. That is dimensionally correct. All right, so here's one of the secrets in physics questions. Nobody's really trying to trick you, but there's a trick sometimes, a strategy to figuring things out. So we have this marathon runner who's running at a steady 15 kilometers per hour. And when the runner is 7.5 kilometers from the finish line, this bird swoops out of the sky and flies from the runner to the finish line at 30 kilometers per hour, and then it turns around and flies back to the runner, wherever that runner is as they're making their way to the finish line, and then the bird turns around again and goes back and forth between the runner and the finish line until the runner is finally there at the finish line. How many kilometers does the bird travel? And you say, I don't know. And so this is a conceptual question, believe it or not, from this peer instructional group. There's a guy named Eric Mazur. He is a professor at Harvard University, and he realized while he was teaching physics that at Harvard University he had a bunch of students come into his classroom who all scored perfectly on the math on the SAT, and all he was doing all semester was reinforcing the fact that they could do math, and he wasn't actually teaching them physics. And so he came up with conceptual questions that would challenge not just the math competency, but understanding what's going on. So I'll bring in one of these every now and then when I think it would illustrate a point. And here it's illustrating a point. If all you could do is math, you might be up a creek here, because if you were going to hammer this one out mathematically, it would take you a long, long time. Because you could figure out how long it takes the bird to get to the finish line, and you could figure out how much further toward the finish line the runner is when the bird gets there. But then you'd have to figure out where the bird and the runner will meet again, and then keep doing that over and over again. It would take you a long, long time. However, there's an easier way to do this. How long is it going to take the marathon runner to finish this race? Well, they're running at 15 kilometers per hour, and the finish line is 7.5 kilometers away. So at 15 kilometers per hour, they'll travel 7.5 kilometers in half an hour. All right. Yeah, that makes sense. All right, so now the question is, how far does that bird who's traveling at 30 kilometers per hour travel in half an hour? 30 kilometers per hour for half an hour would be 15 kilometers. So the link between their two motions is time. And we'll see that over and over again in physics, that we'll be talking about two different objects moving, and the link between them is time. Time will work for everyone. All right, I don't want to terrify you, but the word trigonometry is there at the top left of this slide. We're going to use some trigonometry. It is not as bad as you remember it or heard that it was. It's just not a bad thing. So we're going to do some really simple stuff. We have a triangle. We call this a right triangle because it has a 90-degree angle in it. So two sides of this triangle are perpendicular to each other. That means they're not parallel, that they intersect with a 90-degree angle. And then there's this other side that we call the hypotenuse. So we have the two sides. We call one the adjacent side. It's adjacent to angle theta that we're always interested in. And the opposite side, that's on the opposite side of angle theta. And then the hypotenuse. So opposite, adjacent, hypotenuse, angle theta. This is a right triangle. All right, so here's all you need to know about trig. Well, there's a couple of things. Here's what I would like you to know, is that there's this tool that we have that can give us the relative lengths of the opposite side to the hypotenuse, or of the adjacent side to the hypotenuse, or of the opposite to the adjacent. And so those are our trig tools. So sine theta, cosine theta, and tangent theta give us a number. And so if the angle was 45 degrees, if I did sine of 45 degrees, I get 0.7071. And that would mean that the ratio of the opposite length, this length, to my hypotenuse, it's about 70%, 71%. the length of the hypotenuse. That's all this is telling us. It's just giving us this ratio. So if my hypotenuse was 100 meters, then my opposite length for that particular triangle would be 71 meters. And that's what we're getting out of these trig functions. So sine theta, cosine theta, and tangent theta. So if you're using a calculator, and I would recommend a relatively inexpensive $14, $15 TI-30 kind of scientific calculator, the trig functions are there. Just make sure that you're in degrees and not radians. And if you are confused about how to set that up, make sure you look for a YouTube video. Hey, I've got a Casio calculator. How can I set it into degrees and not radians? And they'll walk you through that. If you have your cell phone, then when you set it into calculator mode and you're holding it straight up and down, you generally just have arithmetic. But if you turn it sideways, you'll get your trig functions there as well. Just try to do sine of 45 degrees and see what you get. If you get 0.7071, then we're in business, and you can move forward with some confidence. All right, so let's say you're standing outside next to a tall building and you're like, gee, I wonder how tall this building is. What can I do? I could get a giant measuring tape and measure the height of this building. I could drop a rock from the top of the building and time how long it takes to hit the ground, but somebody might get mad at me if I hit them with a rock. So what you could do, it's relatively easy. You can figure out how long your pace is, and you could stand up next to the building and walk away from it for a certain distance. And if you know that distance, that's going to be your adjacent value. Now, if you're clever and you have a protractor on hand, I don't know, maybe this isn't the most practical example, you could measure the angle between where you're standing and your line of sight to the top of the building. They're illustrating that as though you would see the sun at that angle, but you could figure out your line of sight to the top of the building. So what you have, we know that tangent theta equals opposite over adjacent. Opposite would be our height, adjacent is our base, and we would figure out the angle is 50 degrees. So tangent of 50 degrees equals opposite over 67.2. So opposite, I'm going to multiply both sides of this equation by 67.2 so that I get opposite all by itself. So opposite equals tangent 50 degrees times 67.2 meters, and I would get 80 meters. I'd figure out the height of this building based on this trig identity. It's not that bad. I know it sounds terribly terrifying. It really isn't. If you have the values for the opposite length and the hypotenuse, you can figure out the angle theta. And that's called inverse sine, inverse cosine, and inverse tangent. And when you do that on your calculator, there's generally a button somewhere to do the inverse thing. So you'd have to figure that out specifically for the calculator that you're using. And then you would get your value for what the actual angle is based on your opposite and adjacent lengths. So in this case we have this fisherman, and we're figuring out the angle for the shore as it drops away into deeper water. I guess we're assuming it's a steady decline. And so if we know that it's 14 meters deep at some point, no, adjacent, 14 meters over and 2.25 meters deep, we can do inverse tangent of opposite over adjacent and figure out the angle that it sloped down, 9.13 degrees. Again, not a great example, just something. All right, so The other piece here, the Pythagorean theorem, maybe you've heard of this, a squared plus b squared equals c squared. So c in this case is the hypotenuse. So h squared, the hypotenuse length squared, equals opposite squared plus adjacent squared. That's the Pythagorean theorem. So if I was told the lengths of my opposite and adjacent values, I could figure out my hypotenuse. I take the square root of h squared, ho squared, opposite squared plus adjacent squared, and then I would have the length for my hypotenuse. Why we talk about this, there's different kinds of quantities. Scalar quantity is something like temperature, speed, or mass. It's just a number with units. A vector quantity has magnitude and direction. So speed, I'm traveling at 35 miles per hour. That's a scalar quantity. It doesn't tell me where I'm going. If I said my velocity is 35 miles per hour straight north, then you'd know that I was escaping to New Hampshire or Maine, and you would have some sense of the direction part as well. So vectors, because there's a direction, that's where we're going to use those trig functions to be able to figure out the direction of a vector, and we'll get there soon enough. We're introducing these concepts here in Chapter 1, so they'll scare you a little less when we get back to them in Chapter 3. When we add vectors together, what we do is the tail-to-head method. This is just like doing a number line from elementary school. If you march out 5 inches, 5 centimeters, and then add on a couple more, that's number line addition. When we do this when they're not lined up in the same direction, so 5 plus 3 equals 8. Now if we do 5 plus 3 equals 8, 5 straight east plus 3 straight north. Now we've mapped out the two components of a vector, the x-axis component and the y-axis component. What we want to figure out is the resultant vector. That's what the R stands for, the resultant. When we add vector A plus vector B, what's the result? If I didn't want to walk 5 meters east and then 3 meters north, couldn't I just go straight from my starting point to the finish line? Why do I have to take this weird route? So, I guess we're doing 6 plus 2. Who knew? 6 plus 2 in this case is going to be a squared plus b squared equals c squared. So the resultant vector is 6.32 meters. So I only had to travel 6.32 meters instead of 8 for my actual distance on my odometer. And I could figure out the angle because I have the opposite and adjacent values. Tangent theta equals opposite over adjacent. Theta equals inverse tangent of opposite over adjacent, 18.4 degrees. Still not done. My resultant vector would be 6.32 meters at 18.4 degrees north of east. So I'd face east, and then I would angle 18.4 degrees north of east and travel for 6.32 meters to end up in the same place as if I had traveled 6 meters east and then 2 meters north. This will make more sense soon. Sorry if I scared you.